Hello, everyone, and welcome to today's webinar, How to Spot and Understand AI Bias Within Financial Services. Thank you all for joining us to discuss a very important topic because as artificial intelligence becomes more prevalent for business use cases, we must be aware of how its outcomes may present biased results. We may have time to answer questions at the end of the discussion, so please utilize the Q&A functionality at the bottom of your screen. To start, we would like to present two poll questions to help us better understand our audience today. So our first poll question is, what interested you in joining today's webinar? Give everyone about 30 seconds to answer. All right, so it looks like the majority of the results for this poll is that people are here to learn more about the topic, but it also is relevant to their role or their team's function. And a few people are also looking for solutions to combat AI bias. All right, moving on to poll number 2. Are you looking to implement AI at your current organization? All right, so for this poll, most people in the audience are already using AI, but we do have a good number of people that are exploring the possibilities. Moving on, our speakers today are Josua Krause, Ph.D., VP of Data Science here at Accern, as well as Anshul Vikram Pandey, Ph.D., Co-Founder and CTO at Accern. And they have also both been teaching about this topic in the Foundations of Data Science course at NYU. So now I'm going to turn it over to Josua to kick off the presentation and get us started today.
Thanks, Brianna. Awesome. Nice to meet you, everyone. Let's get right into it. And so the first thing about bias is like, okay, recently there has been a lot of talk about it in the news, like companies detected that like some of their models were like doing some bad things because their model was biased, which in some cases actually killed some projects where the model was not viable because like it enforced, like, for example, racial bias and stuff like this. So, and it's actually looking at like where in which industries that happens. It's actually ubiquitous among like all industries where AI is used. So healthcare, law enforcement, lenders who make decisions on whether to give out a loan or not, insurance companies, same thing, but with insurance, or even human resources. There was like this famous discussion at Google a while back where it was about like discrimination in hiring and so on. Yeah, so just to give you a couple of like pointers of like where it actually happens and how it has been in the news. So, but I guess let's start with the question first: what actually is bias? So bias fundamentally is having a faulty assumption about your data, about your problem. So there's the idea of how your problem has to be solved in your head, but there's a lot of like unknown factors that can screw your results when doing it. And so that's where bias, that is what bias is, where you basically just need to adjust your assumptions and figure out, okay, where are my assumptions wrong? And there is no way of escaping bias at all. Any system where we take in observations and suggest actions will have some bias. It might or might not be as bad as those examples that we saw before, but it is ubiquitous and especially important when the decision that we make based on those observations can discriminate people, or like on certain grounds, be it legal or or like giving out a loan or not, and especially also if any of those decisions could be interpreted as being unfair towards one person versus the other person, especially if people directly are impacted by the decisions of a model. But again, everything always will have a bias, and sometimes we can actually utilize this bias in a good way, which some people call productive bias. For example, if there's like the notion of like general models that try to solve everything, which might be working well for certain things, but if you go into the nitty-gritty, they often don't behave as well as they should be. Like, for example, let's say a sentiment model that tells you whether something is meant positive or negative works very well in general, but like if you go into specific topics, for example, finance, like what a positive sentiment is might be completely different than a general understanding of positivity. So in this case, we actually want the bias towards a certain category. And in this case, it won't discriminate anybody, but it will actually improve the model. So it's important to keep in mind that bias by itself, you need to think about what is the effect of this bias that I have, and how it affects my outcomes, and whether I want those outcomes to be biased or whether I want to get rid of this bias. And another point is any bias is that exists in data, from labeling or from acquiring data in a certain way, will always be amplified by machine learning models, because the models themselves, they don't have any idea of what they're doing. They see the data and they train, they understand the data, and they give you the output. But there's this famous saying of garbage in, garbage out. If your data is bad, your model will also be bad. So models just can work with what they get fed into. And if you have some bias in your data, it simply gets amplified through the model, because that is what the model is doing. It looks exactly for ways to dissect the data in a way to make an accurate prediction, and that is usually what we want. So we need to be very careful about the data. So just to see bias in a broader context, here is kind of what we would call the data science pipeline. And so what this represents is here in the beginning, we have the world where like reality exists, and we want to make sense of that reality. So in order for that to happen, we cannot look at the whole world at once. You cannot ever have an overview over all the data that there is. So you need to make certain decisions to select down your data, like be it selecting data points, or be it representing data points in a certain way versus another. And this is how we get to the actual data set that we can work with. And then from there, we take that data and use machine learning algorithms to basically figure out, okay, what are the hidden things in this data that can give me a sense of how to make predictions. And in the end, those predictions have a real world impact again. So that's why we start with the world and we end with the world. And so in this data science pipeline, there are now different stages where biases can happen. And so we will be going through each of those stages one by one now. So at the beginning, I already kind of talked about this. We have to make sense of the world around us. And for that, and for that, we need to subset the world, because we cannot work with the whole world at once. Like you cannot fit the whole world on a hard drive. That cannot work at all. So you have to sample down your data, and so there's a certain biases that can happen there, which is selection bias, sample bias. When you have like flawed assumptions about, or like when you have flawed filters for your data, so you get a certain subset of people, for example, that have certain attributes that is not present in a different attribute. And the same happens with the data points that you throw away, the exclusion. Like that's just the other side of the coin. You can also get like a bias by excluding other things. Then there is systemic bias, which means that the world itself represents a situation that you in your head don't think about. So the model and the data just represents this situation, how it is in the world, without you being aware. Like especially common is that, like regarding race, racism and so on, where like data often has like very hidden biases because of how the data was acquired or at which time it was acquired. And time we're going to talk later. So let's focus on data generation. Then there's of course a labeling bias and measurement bias. So you can get your labels wrong. And there's also confounding and latent variables. Latent means like hidden variables, things that we can see, things that influence our data in a certain way. Like there's this famous example where a lab was doing an experiment and they had their lab temperature, like the temperature in the lab was at a certain level. And when they sent their results to a different lab, which had a different temperature in the lab, suddenly all the results were off because they had this confounding latent variable of the temperature that they didn't account for, that it makes an actual difference in their measures. So those are like very subtle things that can sneak in when you're modeling your data. And then lastly, representation bias, which just means how to choose, because like the data is not, the world is not already organized how your machine learning model can digest it. So you need to find a representation that you can fit into your model, and their bias can also happen. So yeah, those are a lot of problems. So let's talk about solutions. And when I say solutions here, it's, I would say 90% of the time, the major roadblock is to actually detect the bias itself. Once you found out the bias, the solution is more about like changing how you acquire the data and like reacting to what was wrong with the data. So there's not really a way to give general suggestions about how to solve it, but it's more about how to spot the bias in your data. And like here we listed a couple of examples, like model label cross-check. So what that means is you let your model predict on the data that you have, and you just look at where the model gets things wrong, and you verify that when the model gets things wrong, it's actually the model that is wrong and not the data. And so we have an example later where that played an important role. The same goes with inter-rater agreement, where instead of labeling only by one person, like if you have data that needs to be labeled, like for example, sentiment or like lending decisions, right? Like if only one person makes the decision of whether or not to give a loan, you will get the bias of that person if you're not too careful. And so having inter-rater agreements, having multiple labels looking at the same data, coming to the same conclusion, can mitigate that bias. And lastly, active learning is a technique where basically you look at subsets of the data in a specific way. So you have an algorithm that suggests you which data points to label to be more effective. And as we said earlier, like you cannot capture the whole world, so you need to make decisions somewhere. And you don't want to label data where the model already figured out what the trick is. Like if the model already fully understands the data, you don't need to label those rows. You want the rows where the model has problems, where there's uncertainties. And active learning is basically a technique to squeeze those points out and label exactly the data that is useful for your task. Yeah.
So on that itself, Yoshi, we are also talking a lot about these days about a data-centric AI, which is all pretty much based on this idea on good data would lead to good models, higher accuracies, and so on. And as data scientists, I think one of the other things we have observed pretty much firsthand is there's always this lack of good amount of training data that we could use to train our models. And a lot of us then venture out in the wild and try to label a lot of that data set. So I know like maybe we don't really talk too much about it out there around how do we ensure higher quality in the labeling process itself. And then what kind of things should data scientists be careful about or watchful about when they are trying to go through this whole data generation process from scratch. So what would be your thoughts there?
Yeah, absolutely. So one important thing is for data, for the data selection is to be diverse, because models cannot really extrapolate from what they see. So you will always end up with the known cases, and if you try to extrapolate, the model will have trouble doing it. Like, for example, if you want to predict the height of a person, it will always tend to go towards the mean of the population, the mean height, if it finds data points that are not there and they're not labeled. It will never suggest like, oh, this person is going to be three meters tall or something. So models tend to be not as good as in extrapolation, and so it's very important to basically find data that is diverse and that covers all the sub categories that you're interested in. Yeah. Okay. Yeah. So then let's move on to the next step in this pipeline, which is now the actual model creation and what kind of biases can sneak in here. So of course, every algorithm that you use for modeling has its own bias that you need to know about and like know how to deal with that. But also learning itself can have biases, especially things like overfitting can happen where you bias yourself towards the training data, and the model basically learns like memorizes the training data instead of learning the general concept, and so it won't be able to apply that to different data. Another thing, outlier is non-normality, which means non-normality in terms of like distribution of your data. Like if the data is not distributed in how your model expects it to be, that will certainly create a bias. Aggregation bias, if you aggregate or filter down data in a certain way, trends can change and correlations can change. Like Simpson's paradox is a famous example there, where if you split data by a feature like man versus woman, like a positive like upward trend can suddenly become downward trends inside those subpopulations. So those are just like statistical things that can happen all the time. Like machine learning is based on statistics. So all the things that can happen in statistics can happen in machine learning as well. Evaluation bias and confirmation bias is all about like understanding how well the model performs. Confirmation bias basically, okay, I see the model is good, so I stop questioning it and I just apply it without thinking further, which is one big lesson there is always, if your model is good, double check that it's really, really good. Because like, especially in finance, like for example, like stock market prediction models, like if you have like a high prediction rate, like let's say even like 70% or something, that should raise all the flags that they are, because that is way too good. If people had like 70% correctness whether the stock is going up or down tomorrow, they would make bang. And yeah, like so you need to always verify that the results that you're getting are actually good and not too good to be true. And then another thing is also, and that we will comment in the next step a little bit in more detail, especially with time series. And we were talking about stock market predictions. Forward-looking bias is an important thing where you normally, when you have data, you want to randomly split your training and test data. So you want everything to be as random and unbiased as possible. But like in time series, you cannot do that because data points from the past have an influence on data points in the future. So if you use data that is from the future for your training, your past results will get influenced, and your model will look better than it actually is. So with time series, you always want to split at a certain date, and everything before that date is your training data, and everything is afterwards is your test data. And we will come to that in the next step of why exactly that is the case. But now let's focus on the solutions for model bias first, and again, solutions here means more how to spot bias in the first place. So one important technique is explanations, like understanding what the model is doing. So there's certain kind of algorithms, certain kind of model that give you the explanation by itself and come up with the explanation, like the model itself gives you insight in how it works. That works very in like more traditional machine learning, but with modern solutions, like we have deep learning and like very deep networks that are so complicated that you cannot really understand exactly how things connect to each other. People try, but like it will never be as good as interpreting a logistic regression where you can directly see the influence. So there's a lot of like black box machine learning techniques out there that don't care what the model itself is, but they just check how does the input to the model and the output that it produces correlate to like trying to explain that directly without looking at the model itself, which works decently well. And like it gives a lot of insight in what the model is doing and how the failure of the model is potentially influenced by that. And another solution is no code AI. So why go out and make all the errors for yourself when somebody made them by themselves before, and you can basically piggyback on their experience. Like, yeah, so somebody already figured out all the kinks and things you need to be aware of. And like with no code AI, you can even suggest to the user, hey, be careful, like if you're using your training data too much, like you might end up overfitting and so on. So no code AI is a solution that is definitely an answer to modeling bias, because you can build on expertise of people who already figured out the solution, and they build all those checks into the software already. Anshul, you sound like you want to say something.
Yeah, so thanks for bringing that up. Yeah, we don't often talk about the human errors that actually happen a lot in the model construction phase. And Yoshi, you and I have gone through that for so many years during our PhDs and then afterwards at Accern, right? All those stories, all those battle scars, that anytime you are getting 55% accuracy on price prediction, there is something wrong. Like look again. But a lot of that is skunk work of, hey, how do you really adjust for calendar years? How do you adjust for anytime you're uploading a data with time series? Your system should automatically kind of stop you from doing random training splits, training test and validation splits. So I think if we ourselves look at our own efficiency of ensuring that we are not really falling in the human error of the model architecture or model construction phase, I would say like that efficiency has definitely increased as we started to pivot our own strategy of model construction towards let's use what's more plug and play and gives us recommendations. But just to touch up further on the human error parts of things. So when we talk about a lot of so human error, as well as the whole point of ML interpretability and ML explanations. We are seeing a lot of these techniques out there, right? Lime, K-lime, Shapley curves, and some of them work in one setting. Some of them already have inherent assumption for the type of model they would work on better. So usually, like, how, for again a data scientist who's really trying to venture into understanding what to look for in my model bias and which ML explanation techniques to use, are there general guiding principles there for them to look out for?
So yeah, like specifically for explanation, as you mentioned, there's some good tools out there. Shapley is like the most popular black box explanation tool right now. So that is pretty plug and play. So you can just use that, like it's a Python package. So yeah, like it's not done by us or anything. It's just like that is the state of the art right now, and it works on all kind of data. It's like it works on NLP, it works on tabular data, it works on images. So yeah, definitely that's a good recommendation here. Okay, cool. So yeah, and I hinted at before, there is a third step where bias can appear, and this is actually only happening in the real world. So the thing is, if you have pictures of cats and dogs, and you want to classify whether a picture shows a cat or a dog, that's not ever going to change. Like once you have a model that works well, it will always work. But this is only like a tiny subset of things in the world where you can apply a model to. And most of the time, actually, what you see in the world is that the world changes around you. And when you train a model, suddenly everything changed and your model is useless. So those are kind of like biases that have to do with time series, but not only time series. Every model is suspected, even if there's no time encoded in it, right? So your data can shift distributions over time, and we will have like an example about where that happened, and regime changes as well. Like things are seen differently from different time points, as well as concepts change. Like a big thing, especially like going back to the original examples that we presented, like racism, historical bias. If you use data from back in the day, you will have different biases than when you use data from today, and you don't have to go that far back. Like data, like the world is constantly changing around us, so you need to be aware of that. And this longitudinal data fallacy is basically what we talked about earlier, about you don't want to like randomly split your data into train and test if you have a time component, because things, and this is the longitudinal data fallacy, is things in the past and things influence things in the future. So if you train on the future, you have this implicit change already encoded, and so your model knows about the future, which it would normally not know about. Yeah, so what are solutions here? Adaptive learning, which is a technique that basically keeps updating models and keeps them up to date without while avoiding to train models from scratch, because like if you do that, if you train a model from scratch, when you see it doesn't work anymore, you're basically starting at zero. So you have to spend like your whole R&D on the model again that you already did before. So you want to keep reusing the model that you already trained, where you know the kinks, where you know how it works, where the fuzzy parts are, where it's not as good. And adaptive learning is a technique that makes sure that this training happens continuously, and like your model doesn't suddenly work completely differently when you train as when you train a completely new model. And the other thing is also like continuously monitoring your model performance. So the moment you put a model into production, that doesn't mean your model is now off and you can do something else. You have to monitor and you have to understand, okay, does the model still hold up with the new data that we get? And because the moment you move a model into production, your accuracy will drop by a tiny bit anyway. Like that is just like the truth of the world. You cannot avoid that. And it gets worse the longer, like the older the model is, it gets worse. Yeah.
So on that, because you said, Yoshi, like the accuracy is almost always drop. I think for majority of us who have been working in the financial services space, that's a real problem. Like if you have trained a model, anytime we talk to model risk folks, especially those who are experimenting with models beyond like regression models and like maybe some of the more recent deep learning architectures, given the black box aspect of it, it's also very difficult for them to really pinpoint why exactly a lot of performance decays happened. But talking about data drift itself, and the need to constant, like to kind of really create utilities and frameworks, if possible, around how do you really, at what time do you say that, hey, my model is now becoming underperformant? And that definition for the audience here, that definition is also not very clear out there. Like if you really ask your business unit, hey, at what threshold of my accuracy would you be calling my model like now underperformant? I think so that definition of what that threshold looks like is very key. And then all the additional steps that are going to follow as a mitigation and rectification strategy also then have to be very, very well thought out. So if I can give this example, so before we wrote this whole adaptive learning framework at Accern that we have talked very publicly about, and like we are also providing lots of those utilities to our clients. Earlier, a very classic strategy to account for model performance decay was just take like a larger set of the data, incorporating the newer data sets where the model became underperformant, and retrain the model from scratch, right? So if you could visualize, it's almost like an expanding window where you keep adding more and more data, and try to build like a model that accounts for this additional data sets. And that technique doesn't really scale well because, I mean, it's kind of constructed to fail, because at some point you are going to hit your resource cap, right? And you cannot then run a single iteration of a model on 10 terabytes of data, right? That becomes very unreasonable. So looking at techniques, so first defining as well as possible, what are our criteria at which we are going to say, hey, now the model is becoming underperformant. Then parallelly looking at creating utilities to look at what kind of distribution shifts and data drifts that might be happening, because again, it's garbage in, garbage out. And then eventually then deciding what kind of mitigation strategies are best for your business to really update your models as well.
Absolutely. So regarding like concrete numbers on when to retrain a model, that entirely depends on the use case at hand, how frequently the data changes, how is the expected drift in the data. Like there, you can monitor the performance and you can look at trends. Like you just have to kind of like look at your problem in detail, and like it's like a baseline basically, right? Like you before you train a model, you train a baseline model to understand, okay, what is the easiest way of understanding your data, and what is the performance of that. And so like having a baseline model, you want to look at that problem the same way, where you set your targets depending on what is expected performance and what is expected like variation in performance as well. Like you can infer that from your training data and like training and test data, since the new data you don't have at that point. Another point you mentioned about like, okay, let's just like increase the data size over time for training. And so one thing of that I mentioned earlier is that that is basically like training a completely new model. So all the assumptions you have about the previous model get thrown out of the window because you train on new data. The second is also you want to finely tune whether or not the model should be more aware of more recent data or more aware of older data. If you only like, if you train it like this without any special like considerations for that, you will have like you bury by like the data, like your model will still be biased more towards the end, because the new data that you have in general is not as much as the old data that you have. And over time, of course, that will change. At one point, you have more data in the new data than in the old data. But like you need to dynamically adjust that and figure out, okay, how do I balance that out? And so yeah, like that's why, like if you just continue training, you need to be careful about how to select the data, so you don't get your data for training biased too much towards the recent data, or too much, sorry, for the old data. Yeah, so I guess that is from this perspective for now. Like we talked about like where can biases appear and what are potential solutions or ways to spot bias. So now I guess we talked a little bit about like, okay, what we actually did, but Anshul, maybe you can go a little bit more over what concretely we are doing.
Sure, absolutely. As Yoshi was describing, like a lot of these are actually coming from also our own learnings. So at the very outset, Accern's no-code AI platform, we built it primarily to offer financial services institutions the ability to utilize some of the most cutting-edge AI models that are out there to extract insights from their unstructured data. So when I say unstructured data, it's primarily text data sets, whether these are reports, news articles, Twitter feeds, SEC 10K filings, insurance documents, and so on and so forth. So this large corpus of text data sets that financial institutions have, which they are storing, but currently fairly underutilized. Our platform helps them analyze it. Now they can then use the output with all the analytics in different manners possible. So the way the whole platform operates is the clients can actually bring their own data. So they can upload data through some third-party connectors. So if you, let's say you have some data set in your Snowflake warehouse or any of the databases, you can upload that data and to analyze. Let's say you are consuming Dow Jones or Morningstar or SEC 10K filings or some of these additional premium sources. We also have those data sets pre-integrated that you can use. And you can also upload like your files from your local file systems, like PDF, CSVs, and so on. Now, once you have selected what data you are trying to analyze, you can also select a bunch of pre-trained models that we have, a lot of pre-trained natural language processing models, like document classification, entity classification, financial securities mapping. So going from iPhone to Apple and Apple's Bloomberg ID, for example, sentiment analysis, relevancy, and so on and so forth. And then you can then send all that output with analytics to your downstream application, whether it is your BI dashboard or you want to consume it in your Jupyter notebooks or to any of the data warehouses. Next slide. Now, given that we pre-train these models, we also have to worry about this whole life cycle that's also susceptible to different types of biases, right? So let's say when we are trying to build a sentiment analysis model for financial services, we have to find representative data sets for financial services. We have to get all of that data labeled through our internal teams who understand the eventual context. We have to create different types of measurements and techniques to really curate that fairly specific data set On top of which, then we are going to be training different types of models and evaluating models and then deciding which models to use. And then once those models are deployed, we again then have to worry about, are there data drifts happening? Are there mentions of new types of keywords that our models might not have seen in the past? So in that manner, we actually have to worry about all those three steps of data generation bias, model bias, as well as the data drift bias. And we're going to talk about a few examples of how the specific problems that we faced, how we spotted the bias and mitigated them, and then some use cases from our end user perspectives.
Yeah, exactly. So as Anshul mentioned just now, like, for example, for our models, we need to constantly label data to stay up to date with like first training the model and then also keeping them updated. And so for that, we implemented like techniques, what we mentioned earlier, model label cross-checking, where you basically verify that when a model gets something wrong, it is on the model and not on the data. And if it's on the data, you need to think about how to improve your labels. And the other thing is inter-rater agreement, where multiple people looked at the data and agreed that the ground truth that they labeled is in fact correct. And so yeah, like we saw a lot of this in our own data that we labeled from our, like we taken data streams, and we for example, we want to build a sentiment model on the data. So we need to look at like we need to label the data and need to make sure that the labels are of high quality. Because if the model, if the labels are not up to standard, especially like if you're aiming for like 90, 95, 6, 7, 8, 9% accuracy, like if the model, like if the data itself doesn't have that accuracy, you will never be able to reach that number. Like you might think the quality is that high, but like you need to take into account the accuracy of the data itself, which might be lower. So it's basically the combination of both. And yeah, so using those techniques, we were able to improve and, like, first of all, spot instances where the data had low quality, and we were able to like reassess those data sets where we had low quality, and yeah, employ like inter-rater agreement as well to just make sure that like everybody agrees. So inter-rater agreement doesn't have to be on the full data all the time. It can also just be on subsets to just like confirm, okay, in general, what is the quality? So like you can do like a multi-stage approach of having first all the data, multiple labels, and then additional checks to just verify that the data, the quality is holding up. Okay, so let's move to, oops, another example. That is, we talked about that before as well, distribution shift. And I think that the best example for this is has been COVID-19. So with the onset of COVID-19, once it came into the news, and we are interpreting and digesting news. So for us, like the models needed to be able to understand that things are different now. Like there's new words, like COVID is completely new word that you haven't probably seen before the pandemic, but also things, especially towards finance focus. Like suddenly you have people that experience hardship that weren't there before, and the reasons for this hardship needs to be encoded into models. So they, like, especially like in cases for lenders, for example, the lending algorithm understands what the situations are, instead of just saying like, okay, no, like we reject everything right now, right? Like you don't want that. And yeah, so another thing is like, for example, like stock market prediction. Suddenly, like stock market in the last 2 years have been, like people say, have been crazy, but like the fundamentals of how it works have shifted in a significant way for multiple reasons. Like also, like if you think of things like GME, like that completely goes unexpected. So you want to be able to learn from those changes and understand them. And yeah, we talked about this before. Adaptive learning is a good solution here, that is able to keep your models up to date without having to retrain them from scratch. Yeah, and that in general will prevent you from experiencing performance decay.
So on that, one more interesting example that just came to my mind. So Yoshi, just extending a little more on this peer-to-peer lending firm that you're working with. So their underwriting rule book was pretty much based on past, historic bank balance data sets, right? Like the transactions data that we were looking at, suddenly during COVID-19, like every small medium businesses bank accounts were slumping. Like the people are going to negative bank balance, and suddenly all of those underwriting rule books had to be updated to account for this significant regime shift that was happening. And I think that's where we saw techniques like adaptive learning getting adopted just so much across, like I would say, like across the data science landscape. Because everyone was trying to find a solution that is more systematic, and so that they don't have to worry about re-updating all the rule books again. And at least there's something that automatically adjusts. So yeah, so that just looking at that success story from that client, it was pretty interesting to see that, hey, like they were able to like update all their rule books, which were static rule books, to something that was more dynamic and adjusting to regime shifts.
Yeah. Agree. And yeah, speaking of clients, let's come to our third example. So here we had like a big bank approaching us that also was in the business of giving out loans, and the issue that we identified here with the models was that their data was not diverse enough to be able to accurately reflect the businesses they were trying to give loan to. And so what happens on their side was that they rejected the loans prematurely, basically. Like the model just didn't accept any of the loans, and they were looking at it and saying like, okay, like what is going on here? So this is where we could provide from our like large selection of news sources and additional information, we were able to give them and create them a more diverse data set that takes all the additional facets into account. Yeah, and since then, at least at the time for writing this, like 150 plus small business loans have been given out. And that is a success story. Like that wouldn't have been given out, yeah, like just because the model was discriminating against those businesses because there was not enough information for the model to know that those businesses are fine and are solvent enough, like are good enough to be able to be given a loan. So yeah.
And I think like just if you think about this diversity in data set problem, I think it also then relates back to the systemic bias that we were discussing. Like, where are these sensors really deployed, or these data collection mechanisms really deployed to collect the data? There are, if I talk about also healthcare, like most of the healthcare data that's out there is from California, New York, and Massachusetts, not very representative of the whole United States. And that is also very similar, a case even with a lot of these data sets that people are using for underwriting loans to at least build their models. So that just by adding that diversity and like thinking about these alternative data sets that they could bring in, you could immediately see good impact and new impact in the space. And that is a perfect segue to the next slide, because not only companies are realizing this, but even regulatory bodies that are out there, that they are coming up with frameworks that actually emphasize a lot on the fairness in the whole process that we talked about, right? And as we said, it all then converges down to the data that you are going to be using to train your models. So European Commission, you might be well aware of the report that they published recently. Federal Trade Commission also pushed out like a proposal to regulate AI. We have Federal Reserve systems that have also come up with it, and FDA as well, right? So if you look at the regulatory bodies in the government, there's a lot of participation there. There are also lots of call for proposals, call for inputs from communities, where even startups are providing inputs and saying that, hey, like the way you are thinking about ML interpretability, it is not going to scale when you are going to build models with 1 trillion parameters, right? Just by showcasing the feature importances of each models, it's not going to solve those problems. So there's lots of active communication. And then on the other side, if you look at even the private companies, a lot of private companies are also coming up with their own frameworks and proposals to define ethics and fairness in AI. So with that, let's go to the very last slide, and then I think we'll have some time for questions. The key takeaways: bias is ubiquitous. Some of this could be used productively. You just have to be careful about what bias you're comfortable with and what you're not. You just cannot ignore it, because if you ignore it, some projects get killed in a very public and drastic fashion. And it has to be dealt proactively, even if that dealing mechanism means, oh, I'm going to ignore this particular type of bias. But with that, let's open the floor for some questions, and we can talk about some of those.
Yeah, so thank you so much, Yoshi and Anshul, for that presentation. I do see we have 2 questions here. Anshul kind of answered this first one, but if you just want to dive a little bit more into the question of, what if the data is too private to upload? Do you have a method of downloading the system so the data can stay safe?
So like there's ways of anonymizing data, but like, of course, that is always like a tricky thing to do, because you cannot fully remove all personal identifiable information from data if you upload it. Like, for example, if you're thinking healthcare, like there's no way of removing the personal information without losing accuracy of your model, right? Because like the moment you remove something, the model is not going to be able to deal with that. So for that, like employing systems in an on-prem basis is a way to avoid that. Like just like dealing with that in-house and just like getting the tools pre-made into your own company. So like you don't have to trust an outside source with your data. I'm sure you want to.
No, I think that part, and then of course there are now techniques available where the whole life cycle of the data getting uploaded, processed, analytics coming out. There are now good toolkits that and techniques available that in the Accern platform also we have integrated, which like just assigns a key for you that is only private to you. All the data that you have ever uploaded will all be encrypted. Even Accern cannot see it, and of course no other clients can see it, and so on. But yeah, like I think today we are at a stage where the data privacy problem is there are good solutions out there, and we don't really see AI projects getting halted, because in the worst case or the extreme case, you can just take a whole system and deploy it in-house on-prem. So that's also fine. So now there's a question around do you consider models that are aware of protected attributes like race and gender work better than protected attribute blind models, like models that don't even see race and gender. So any thoughts, Yoshi?
So I would say like there's not a one size fits all answer to this. It depends a lot on your particular problem, but in general, withholding information is gonna affect your model in a way. There like so if you withhold the race and gender, there might be some connections that are made using race and gender, which are sometimes even important. Like there's like, especially like in healthcare, certain races have like completely different sets of diseases that they can deal with. Of course, you have to be careful. Like if you look at it from a healthcare perspective, from the physician who tries to cure the person versus an insurance company, there might be different interests in both stakeholders. So yeah, you have to be aware that if there are hidden connections with race and gender, it might be beneficial to know about them and be able to deal with them, or like if you remove them, like it might be more fair. That depends entirely on your use case.
Yep, and also like another thing you may want to, again, every time we think about bias, especially in the data, we have to think a little like more holistically. So if I take the Apple Card example, right, like where Apple Card was issuing lower credit limits to women versus men, apparently it was that the actual model never even saw gender as a feature, right? But there was a credit score as a feature that was getting learned. So after a lot of this scrutiny, what they came up with was the actual system to assign credit scores. There is more of a systemic bias, which actually leads to lower credit scores for women. So once again, thinking about bias more holistically and more than just a particular feature, and also thinking about all the other features that you have in your data frame. Are there potential associations? That will be like also a recommended way to think about it.
Yeah, like that is kind of like the on the earlier slides, there was the confounding variables and the latent variables that have an effect on your like, and you can have data leakage between features as well, as Anshul just mentioned. Yeah.
I think we have a few more. Any particular data bias that we come across in financial services more often than the others? I would say the data drift is a very, very common one. It's almost every single time we see, every client we work with. If the model is not adjusting to the new knowledge, that becomes very difficult for them to really justify the eventual ROI. But Yoshi, any thoughts there?
Yeah, like you could almost say like it's the current meta, to use like different set of terms. That is definitely one thing. Another thing, especially lending, it's always like, yeah, like protected attributes play a big role. Like you don't want leakage there. So that is a bias that you want to be aware of and like get rid of and be proactive about like resolving it. Yeah.
And diversity, absolutely. Like diversity, yeah. I would say it's really at the crux of it. We have a question from Avery. Key statistical methods to challenge various biases in sentence or two for each bias. For example, resampling to selection bias, using z-score threshold to prove, or is it too case specific for other biases?
Resampling selection bias. So statistical to challenge resampling using z-score threshold to prove. Yeah, you can do also like kind of like bootstrapping to understand like the variance inside your data, or like do like k-fold segmentation of your data, where you just like look at smaller subsets even. That is one way to understand, okay, what like that is not the way to understand like how the training data behaves with with respect to the other data, but like inside the training data, you can see, do you have any subset of there? So the moment you have data selected, you cannot regain the data that you threw out, right? So that's why you need to like, you can only look at your, if you want statistical methods, you can only look at the data that you already have. Like you could look at the broader data that is beyond that, but there the question then becomes, so if you have a way to look at the broader data with like appropriate labels and everything, then why not use that bigger data set to begin with, right? So like in general, the data you said you use for training, like you kind of can assume that is the size you can afford to get. Like getting labels is also like expensive and so on. So you need to work on that. And so that's why my answer mostly revolves around like, okay, subsetting the data that you already have further and analyzing it, whether there's some occurrences inside the data that are unusual. Or another technique is also like that goes more towards like model cross-checking, where basically you can look at the distributions of the predictions with respect to the distribution of the labels, and see if something sticks out as highly unusual. So I, like, as part of my PhD, I wrote a paper about this. That's like many years now. That was about healthcare, and like basically what we found was that in the data that the machine learning model was trying to make a prediction based on the fact that somebody got a CT scan, but not knowing the outcome of the CT scan. So which was just which is exactly this problem, right? Like so the model is trying to make sense of that, and looking at the distribution of the predictions, we saw basically that the model just chose the more frequent class in this case, because it didn't know about the outcome of the CT, and like the whole thing about like doing a CT in the first place is because you don't know what is going on. So trying to just predict something on the basis of a test that was ordered, where the test is indicative of the uncertainty, you have to rethink your labels there, and so that's I guess like one important thing in general is sometimes the data that you have is just not enough, or sometimes it's just like incorrect, like not incorrect, but more like you need to rethink the problem. So that's kind of like the data science flow is always like going back, like you learn something about your model, and then you take that new knowledge and apply it back to the beginning of the process. And maybe like if you can afford it, you can like get new data. So it's always difficult to get new data because it's inherently expensive. So like unless you have a thing like a stock market where you can just infer it from the data itself, but like typically you need to get your labels from somewhere, right? Yeah, so I hope that was exhaustive enough.
Yes, well, thank you so much for that insight, Yoshi and Anshul. And I know we ran a little bit over, but I also wanted to thank all of the attendees today. There will be a recording of this webinar on demand available after the session. So with that, everyone have a great Wednesday.